Okay. Okay. So guys, there. 1, 2, 3, 4, 5. Okay. So almost one of you are there. So people. So if you can remember what you're seeing, right? So we were seeing about intermediates, right? So we'll continue, right? So I think I just introduced you to this inductive effect, right? So with respect to inductive effect, we decided carbocation stability, right? And then we even did. I told you that inductive effect can be done only for charged species, right? If you want to talk about charged species, at that time only you can use inductive effect. So indirectly, you cannot use inductive effect for free radicals, right? So that's what we said. And then we went on to see how do you determine the stability for carbocations, carbanions. We said we can have plus A effect, minus A effect, plus A effect, electron donating group, minus A effect, electron withdrawing group, right? So based on all this stability criteria for anything would be lesser charge, more stability. Charge and amount of stability are going to be inversely related, right? So that's all we did last class. Right? So we'll continue and hope you all know that today will be a 2 hour session. So I will take till 11 to 11:15 will be a break. And again from 11:15 to 12:15, we're going to continue the class. In the same link, you just have to switch off the video, mute yourself, keep your phone, go do whatever you want, have a coffee, take some snacks or whatever it is, and we'll come back with 10 minutes. Is that cool? Right? So we will continue. Right. Fine. So where else we'll be using inductive effect is the question, right? So I told you it is not only about the stabilities of carbocations and carbanions when we're using it. So even in case if you want to decide, I give you two carboxylic acids, right? And I ask you to decide which is more acidic, which is having more acidic strength, which can give me more H plus, and all those questions if I ask you. So again, on those cases, inductive effect can be used. Okay, so how we will try to see, right? And even the basic characters, like you should study in your amines chapter, right? How do we decide the basic character of amines? So again, there also inductive effect is used, right? Okay, so we'll start with that. Okay, so fine. So we are going for acidic strength first, then maybe we'll go for basic strength, right? So we are going to just use inductive effect. That's it, right? Fine. Again, acidic strengths can be decided if even with the help of resonance. So at that time, we'll see how are you going to do it. Is that okay? Right. So fine. So if I just take any carboxylic acid for that matter, right? If I take any carboxylic acid for that matter, I know the functional group is going to be COOH, right? And obviously H plus can come out from that, isn't it? So before even moving on to this, right? So let me ask you this question. So I have HCl, and say if I have HCOOH, right? Now, which do you think is a stronger acid? I have
HCl.
methanoic acid, HCl. Why?
It displaces the hydrogen atom easily when dissolved on water.
Why? I understand. Yes. So if at all I dissolve, say 1 gram of both of these in water, definitely from HCl, the H plus concentration is going to be higher. Yes, that I understood. That's why it's a stronger acid. Why? Why is that happening? Why are these happening? Any guesses somewhere?
So because HCl is a polar bond.
Even OH. So if I look at the structure here, I mean, this is a polar bond only. Actually, this is more polar than HCl because oxygen is more electronegative than chlorine, right? What else could be the reason? Okay. So the thing is, people, right? So it is sometimes. So I would say there are two main properties for you to decide as to extent. So we'll speak about this in depth when I go for ionic equilibrium. So we are 11th class chapter, and that time we'll spend more time on this. Like in our like in organic chemistry, we'll be restricting our discussion only to organic acids like carboxylic acids, alcohols, phenols, or even alkynes are acidic in nature. So we'll restrict discussion to this only organic molecules. But if I want to go for inorganic molecules like HCl, H2SO4, HNO3, all these things, you want to decide the strength, right? So the parameters are going to be almost similar, but here I would say the parameters are a little less which you have to use. But if you go for inorganic acids, there are still more aspects which you have to look at, right? So if for the first thing would be the bond strength. Bond strength of what? Bond strength. So wherever the H plus is going to come, right, from whichever atom the H plus is going to come, how strong this bond is matters, isn't it? Right? Obviously, from a weaker bond, right, from a weaker XH bond, H plus can easily be removed, right? So obviously now this is what the criteria here. I have HCl bond, I have OH bond, right? Obviously, I know OH bond is more stronger. It's stronger than ClH bond. Again, as you said, the polarity is the reason. More and more is the electronegativity difference between the bonding atoms, right? More and more will be the strength. That's how it is, right? So HCl bond is little weaker when compared to OH bond. So obviously from HCl, H plus can easily come out. That is the first criteria, right? Okay. Now the second criteria is we have already seen. Can someone tell me what will be the criteria? We already saw it for this is specifically for organic substances, right? So what do you think is the criteria? We already discussed it. Nobody remembers. Okay, let me tell you. We saw this in tautomedicine. When I explained tautomedicine, I told you, this is how you decide the strength of acids. What is the criteria? Yes, still thinking. Okay, one more clue I'll give you. Something to do with the conjugate base. So what I understand is, right, either you're not practicing, right? And obviously, please understand, people, we have given a very small amount of time, right? So to complete both 11th and 12th syllabus. So I know that I'm going a little fast. So inductive effect will itself take almost like 3 hours if I teach you properly. But again, we have since you have already learned it, so I know what you know, what you don't know. So those areas only I'll be touching, and obviously there and there I'll be telling you, right? But the thing is, since we are doing this course at a very short point of time, right? You just listening to classes are not going to be enough. Obviously, you have to go and do problems. That is not what I'm talking about. The thing is, the videos which are available to you, recorded videos, you have to go through it as regularly as possible, right? So because you have to keep in touch. If you're not going to keep in touch, say today I'll teach you, maybe 10 days you'll remember, but 20th day you will not be remembering, just like as what exactly is happening here, isn't it? Right? So please be like, please utilize all the resources you have for you very carefully. Right? So many people will not be even having these resources, and still they'll be doing something. Now that you have the resources, why not take advantage of it? Why not exploit it? Right? So please do at least I would say daily 1 or 2 videos. Right? Obviously, you would have completed at least so many videos. At least daily one video. Right? So make sure you're going through and keep in touch with this. Or if you're really good at going through a book and studying, at least do that. Keep it, like organic chemistry is one thing, and obviously chemistry as a whole is actually a thing which you have to keep constant touch with. It's not like 1 month before you study a chapter you'll remember it, but physics, yeah, it's possible because it's all about logic. It's all about some applying formulas and mathematical equations, right? But chemistry is not that only. That is also there, but it's way more than that. Right. Anyways, so if the second criteria would be the stability of the conjugate base. When I write CV talks about conjugate base, right? What is a conjugate base? You tell me.
Sir, you take out the hydrogen of
Okay.
the molecule will be whatever is the remaining part is the conjugate base.
Yeah, correct. Right. So after removing H plus, whatever is remaining is what is called as my conjugate base. Right. Say for example, if I remove H plus from this, Cl minus would be my conjugate base of HCl. Now in this case, after removing H plus, HCOO minus would have been the conjugate base of my acid HCOOH. Right. So after removing H plus, whatever is remaining is what is called as my conjugate base. So the criteria for having high acidic strength is that the conjugate base should be highly stable, and more is the stability, more and more will be the acidic strength. Okay, fine. Now, if you look at this criteria, if I take this criteria for HCl and HCOOH, right? So if you see what is going to happen, if you look at the conjugate base, just I have Cl minus and COO minus and a H. Yeah, right. So this is what I have as the conjugate basis for the cases which we took. Right. So if you look at which is more stable, right? Which anion do you think is more stable? Cl minus or this anion?
Cl minus,
Why?
because it has a complete octet. No?
Octet. Okay. This also has a complete octet. Everything has a complete octet. Correct. Oxygen has having 6 plus 1 7, and one more electron is coming from carbon. So yeah, 8 electrons. Everything is octet satisfied. Hydrogen is duplet satisfied. So what else?
Sir, in I mean HCO minus,
Hmm.
one oxygen will have one free atom, no, sir. Electron, no, sir.
One free electron.
I mean,
See, so you're
one
telling
unpaired electron. When
one
the
unpaired
hydrogen
electron. Tell
when
me.
when hydrogen is removed from that OH bond,
Hmm.
oxygen will attain one unpaired electron, no, sir.
Okay, see, that will happen if, say, I have the OH bond and if it undergoes homolytic cleavage. But here it's not like that, right? I have two electrons and both these electrons are going to go to oxygen, and H plus comes out with no electron, literally, right? So, no, that is not the answer. So, I mean, you don't have any unpaired electron. It's not a radical, no. If you look at the structure, maybe I will have three lone pairs, right? I have three lone pairs and, oh, wait. Three lone pairs and one plus, correct. Three lone pairs plus one plus negative charge will become each, correct. Okay. So anyways, octet is not the criteria, people. So the thing is, if you can think broadly, right? So let me tell you that. So I have Cl minus and I have COO minus. Now what I don't see here and what I see here is resonance. Okay, both are anions, right? Both are having octet satisfied, no doubt about it, right? But the thing is, this is possible, right? I'll be able to rewrite the structure as O minus and a double bond O. So this is possible. Okay, resonance is possible in case of the carboxylate ion, but Cl minus nothing. So definitely, which is more stable? In this case, this is what is more stable. HCO minus anion is more stable than Cl minus, right? But that is again contradicting the statement what we said. We said that more and more is the stability of the conjugate base, more and more is the acidic strength. That's what we said, right? But the thing is, which process happens first? The thing is, for you to form these anions, right, for you to form the conjugate bases, the first step is to break the bond and remove the H plus. Only then you can even talk about the anion, and only then you can talk about the anion, the stability, right? So the first and foremost thing is about the breaking of the bond, or how strong the bond is, and obviously less and less acidic that particle will, that acid would be. And if at all you want to compare two carboxylic acids, I have HCOOH and I have CH3COOH, right? At that time, exclusively you will be using only the second criteria. Second criteria would be the stability of the conjugate base, right? So whenever you have two different atoms present, the XH, if the X is different, then first thing what you have to look at is the bond strength. Then, if at all you say that OH is there in both the cases, then you have to go for the stability of the conjugate base. Okay, so in this case, even though this is more stable, HCl is a better acid because HCl bond strength is weak. This bond is stronger. Everybody understood, I guess, right? Okay, so anyways, this is just an introduction. So we'll move on. So we'll move on to see different carboxylic acids and how are we going to decide. Okay, say I have CH3COOH and say I have CH2ClCOOH and say I have CHCl2COOH. Okay, so I have all these three things with me. I think you have studied it, but still just revision. Okay, so tell me if I mark it 1, 2, and 3. Can you arrange them in the order of acidic strengths? So what you have to do first is the question, right? Whenever they ask you for acidic strength of carboxyl, not only for carboxylic acid, for any acid in organic chemistry, right? First thing what will you do is remove the H plus and make the conjugate base, right? So you will remove all the H pluses. So I make the conjugate base. Then now I check for stability, which is more stable, which is less stable. If I can do that, then done. The process, whichever is more stable, is the one which is having most acidic strength, maximum acidic strength. Right. Now, yeah, go for it. Tell me. So you know what is the stability for criteria. Sorry, criteria of stability. Right? Higher charge, less stability. Less charge, more stability. Now go for it. Tell me the answer. I don't think it's that difficult. Any guesses? No guesses also. Even if it's wrong, it's okay. Just give me a guess.
So is it 1, 2, 3?
1, 2, 3. Which is greatest?
3 is greatest.
3 is greatest. Okay. Any reasons you think what it might be?
There's
Yeah.
2 chlorine atoms.
Okay. So
two chlorine atoms, will they propel inductive effect?
okay, inductive effect. Yes, we are going to use inductive effect here. So chlorine atom is what in the group?
Electron withdrawing group.
Yes, chlorine atom is electron withdrawing group. Okay, so if it's electron withdrawing, what is going to happen in this molecule? Or if you want me to ask you a specific question, what will happen to the negative charge on oxygen if I have chlorine?
So that negative charge will go to the chlorine. It will attract the extra electron.
So yeah, like the correct way of what you said, I understand what you're trying to say. So the correct way of putting it is the negative charge on oxygen decreases. As simple as
Yes,
that.
sir, yes, sir.
Can I put it that way? Right?
Yes, sir.
It's not going to transfer to chlorine atom as such, right?
Yes, sir,
But definitely, but the negative charge on oxygen atom is going to decrease because of the presence of an electron withdrawing group. Good. Yes. Right. So I hope everybody is able to understand, right? So it's all about which oxygen atom, in which case the oxygen atom is having the least charge, right? So obviously electron withdrawing groups, right, are going to decrease the, like how did it in carbon ions? Like carbon ions, what you did, you say exact, you had the exact same procedures, right? Wherever you had least charge on the carbon ion, least negative charge on the carbon ion, that carbon ion was the most stable one, and that's why we said that primary carbon ions are more stable than secondary are more stable than tertiary. Why we did that? Because we said that all the alkyl groups are electron donating in nature, right? So thereby increasing the negative charge on carbon, right? So anyways, in this case, okay, let me take the first case. First case, I have nothing. I just have a CH3, which is going to be an electron donating group, right? So what is going to happen to the negative charge on oxygen? It is going to increase. The charge is going to increase because of the electron donating nature of this, right? Okay, now here I have one chlorine atom, right? So definitely the electron is going to get pulled. Not exactly the electron is going to get pulled. The negative charge on the oxygen atom will decrease, right? And here you see I have two chlorine atoms. So definitely the negative charge is least in this case. So the order of acidic strength, right? Everybody understood why is it like this? Please give me a yes, everybody.
Yes, sir.
Sir.
Okay, fine. So now we'll take, so okay, now if I want to compare this CH3COOH with HCOOH, which is more acidic? Same procedure, right? So out of these two, which is more acidic?
HCOH.
Good. Why?
It's because in the first case, CH3 is an electron donating group, so it's less stable.
Absolutely. Yes, that's the reason. Right. So here I have an electron donating group, which is going to increase the negative charge on oxygen. Here I have nothing. It's just hydrogen. I cannot consider that as an electron withdrawing group or an electron donating group. So here I have nothing, but here I have electron donating group, which is going to increase the negative charge. So definitely HCOH would be a better acid compared to CH3COOH. Okay, right? And people, like what will they generally do is they will give you these acids, like any kind of acids for that matter, and they will ask you to arrange them in the order of pKa values. Some bells are getting ringed, isn't it? pKa. Where did you study this?
Sir, in equilibrium last year. 11.
Okay, very good. Right. So we studied this in equilibrium. So it's basically the negative. So pKa is basically negative log of Ka. Like whenever this P comes, pH, pKa, POH, whenever you see this P, so this P basically means negative log is what you have to put. pH is negative log of H plus. pKa is negative log of Ka. So anyways, we'll speak about this in depth when you go for ionic equilibrium. Now, what you have to understand is if they ask you to arrange these acids in the order of pKa values, you have to be very careful. What you have to understand is pKa and the acidic strengths are inversely related. So a strong acid will have very small value of pKa. Same with H plus, right? Same with pH. What happens in pH? If I have a pH of an acid of 1 and I have a pH of an acid of 2, obviously I know pH of an acid 1 is more stable, right? pH of an acid of 1 is more, not stable, more acidic than pH of an acid 2, right? So same goes here. When I ask you to arrange them in the order of pKa values, the order will be exactly opposite. 1 will have maximum pKa, then 2, then 3. Right? Be very careful with this, right? Okay, so that is about the acidic strengths. Okay, now I can give you more examples if you want. Right? Okay. Fine. I think this should be sufficient. Yeah. Can you tell me if I mark it 1, 2, and 3? Right. Tell me the acidic strength arrangement. See, in your JEE exam, from this area, definitely one question will come for sure. Either this or basic strength. Using this, like determine the order of acidic strength, basic strength. Definitely one question is going to come. There is
Sir,
no, I have seen no paper. Yeah. Yeah, Kanan, tell me.
is it 1, 2, and then 3?
One
Like
is
one
highest or lowest?
highest.
One highest. Okay, good. Right. So yeah, that's the answer. So I think it's very easy, right? So it's all about now. I have in all the cases I have electron withdrawing groups, no doubt, right? But in two cases I have chlorine, and another case I have fluorine. Obviously, I know fluorine is more electronegative, right? So definitely fluorine will be more electron withdrawing than chlorine. Is it not? So if I so this is not even in the picture because I know inductive effect is distance dependent, right? So it's almost like two carbon atoms away, the electron withdrawing group. So definitely the maximum negative charge is going to be there on oxygen. In this third case. So 3 is the least, no doubt, right? But when I want to compare 1 and 2, F is more electron withdrawing than chlorine. So definitely in this case, I'm going to have the least charge, and in this case, little higher charge. So this would have been the order of acidic strengths. Right? Simple, isn't it? Okay, so this is how you use inductive effect, right? Okay, now we will take some alcohols if you want. Okay, now let me ask you this question, right? So we know phenols are highly acidic, right? Okay, right. Let me do that for you. So when I compare a phenol with, say, a carboxylic acid, right? Now think and tell me which is more acidic. Or you don't have to think and tell me what do you think is a guess would be for a higher acidic strength?
Phenol.
Phenol. Okay. Anybody wants to count? Oh, okay. Well, let me take a vote. Right? How many of you say it's phenol? Just give me a guess. I'll just count it. One guy already said. Then
Yes, sir.
2. Okay. So only 2 votes for phenol. Okay. How many of you think HCOH is the better acid?
Sir, I think HCOH is a better acid because phenol has a better ability to resonate.
Phenol has a better ability to resonate. Okay. And anyways, we'll come back to the reason later. So you're saying that HCOH is a better acid, isn't it?
Yes, sir.
Yes? Okay. So 1 vote. Then, anybody else? So rest of you don't want to answer. It's just a guess. It's just a voting game.
HCOH.
Just give your answer. Okay. Second vote. There are almost 6 people. There are 2 more. Please don't make me call names. Okay. Someone has texted something. HCOH. Okay. Third vote. 1, 2, 3. One more. One more guy is missing. Who's that? Okay. Sanjana. So said it's phenol. Okay. So basically, I got 3 and 3. It's a tiebreaker. So that means my vote matters, right? And my vote goes to HCOH. Okay, fine. So this is actually a very not complicated question. You have to little bit know about the resonance here. Okay. So the thing is, people. So as you said, definitely phenol. Like say, if I draw the resonance structures of phenol, say I have a O minus, right? So obviously, I'm talking about the conjugate basis, right? So guys, please understand. If I want to talk about resonance in acidic strengths, right? So what happens is in this case, what happens is the negative charge will come here, this will go here, this will go here, this will go here, again it's going to go back, all these things will happen, right? So wherever you see the negative charge is getting dispersed, that is, it is moving, that means the negative charge on oxygen is getting decreased. This is not true resonance. It is going to go, the lone pair is going to involve, or the negative charge is going to involve in resonance in the benzene ring, isn't it? Right? So definitely I would say that this anion is little stable. So definitely it's a good acid. Okay, but when I compare it with this, say I have a negative charge, right? So please, generally what we do is more amount of resonance structures, more number of resonance structures, I would say that that particular molecule is more stable. Okay. Now in this case, what happens? Say I will come here, this will come here, this will come here. So I can have in this case only almost two resonance structures. One is this, the other would be this oxygen atom having a negative charge and this oxygen atom having a double bond. Right? So only two resonance structures are possible. Right? But here, so many resonance structures are possible. Okay. So generally, what do I think is that phenol will be a better acid. That's what I think, because here I have more resonance structures, so more stability. That's how it is. But in this case, less resonance structures, less stable is what we think, right? But for resonance, that is not the criteria. That is one of the criteria. But more than that, more than the number of resonance structures, right? One more thing matters. The thing which matters is what are the type of resonance structures I'm going to get, right? That means if like this, if I'm going to get two resonance structures only, but both of them are energetically equivalent. What do you mean by energetically equivalent? That means you can see that the there is one double bond oxygen, there is one oxygen having a negative charge, so the next one also is going to have same, right? Say O minus and a double bond O. So these two will have exactly same potential energies. Okay, because the structure is not even changing, right? But here, if you check at a point of time, say if I draw the resonance structure, I have a O minus. Say this will come here and this will break. So the resonance structure would be double bond O and a negative charge, and this would have come, right? So now what do you see? The negative charge itself is actually changing. First it was on oxygen, now it is on carbon. Again, it will go back to oxygen. So none of the resonance structures are energetically equivalent. That means they are not going to have same potential energies. Okay. Now the thing is, if because of resonance the molecule is able to produce more number of energetically equivalent structures, that particular anion or that particular ion is more stable. That's what you need to understand. Okay, so more stability will happen when I have energetically equivalent resonance structures. Okay, so more and more are the number of energetically equivalent or energetically same resonance structures. That resonance is more stable than even if I have so many number of resonance structures with different energies. Okay, so this phenol has more number of resonance, agreed, but none of the resonance, almost okay, most of the resonance structures are not going to be energetically equivalent. But here I produce only two, but both of them are energetically equivalent. So this is more stable than this one. So definitely HCOOH is a better acid than phenol. Okay, right? Anybody has a question? Right? Anybody has a doubt how it happens, or you want to repeat it again? How is it?
No, sir.
Okay, cool. Right? So this is one thing. Actually, there are so many things. Oh God, how am I going to compare this? Fine. Right. That is one thing. So we'll go for different alcohols. So we saw different carboxylic acids, and we decided how are we going to decide the stability. Exactly same way we'll be able to do it for your alcohols also. Like, but nothing much different. Here I was having COO minus. Here I'm just going to have O minus. That's right. So again, I can have say primary, secondary, tertiary alcohols, right? Say something like this: CH3, CH2OH, or say CH3, CH3OH, and say CH3, CH3, CH3OH. Okay. Now tell me, say if I mark it as 3, 2, and 1, right? Which do you think is more? Arrange them in the order of acidic strength. Again, the moment you see the word acidic strength, the first thing you will do is remove the H plus and make the conjugate base, and then you check for stability. Go for it.
Sir, is it 3, 2, 1?
In the sense, 3 is greatest or 3 is less? 3 is the least.
Is greatest.
3 is greatest. Okay. Yeah. So we'll see that. So I have O minus, O minus, O minus. Right.
Sir,
Fine. It's all about.
I say it's the other way
Yeah,
around.
tell
Sir.
me.
Same order, but 3 is least.
So 3 is least. Okay, we'll see which is correct. Okay, so it's all about having least negative charge on oxygen. So wherever I'm going to have the least negative charge, there is the answer. That is having the maximum acidic strength. So it's easily understood, right? I so many electron donating groups here. There's a big electron donating group, CH3, CH3, CH3. All of this will donate electron to this carbon, and this will eventually donate electron to this oxygen. So maximum negative charge is going to be there in this tertiary alcohols, right? And obviously here I have just one carbon atom, one this thing, and obviously it is going to go here and it is going to give it here. So there is less or the least negative charge is going to be there on this oxygen. Obviously, lesser charge, more stability. So the answer is 1 greater than 2 greater than 3. Understood? Right? I think one guy who
Yes, sir.
told me the opposite. I think you understood whatever it is.
Yes, sir.
It's all about the least charge. Very, very, very simple. Anyway, we'll get the hold of it. Again, I can put what to say? I can put what is that? Some chlorine atoms and stuff. Then again, you can tell that okay, if at all I have electron withdrawing groups, again it is going to give me more stability for the conjugate base and definitely more acidic strength. The same thing what we did in carboxylic acid here also is possible. Is that okay? Right. So this is for alcohols, and if I want to compare an alcohol and a phenol, right? So definitely, if at all I have alcohols, just now you saw there is only inductive effect, right? But when I go for phenols, after removing the H plus, there is going to be resonance structures coming. So okay, now you can ask me, sir, if I have if I have a case, right, where I'm using resonance, right, and as well as some inductive effect is possible because there are some electron donating, electron withdrawing groups, right. Say through inductive effect, I'm finding that that particular anion is unstable, that it is not that stable. But through resonance, I find it more stable. You will definitely see situations like that. So through one effect, through inductive effect, you may see a different result, and through other effects, say resonance, you will see an entirely opposite result, right? So on those times, which you have to give priority, blindly give priority to resonance, blindly. Whatever you're gonna get out of resonance, that's the answer, right? So the priority has to be given to resonance when compared to inductive effect. And I'm going to see one more effect called hyperconjugation, right? So inductive effect would have been the least priority. The next priority actually goes to hyperconjugation, and the highest priority will go to your resonance, right? So blindly you can just follow this. Resonance is having the maximum priority, then hyperconjugation the least priority. If you have nothing and just inductive effect to work with, then only you will work with inductive effect. Is that understood? Right? Okay, so obviously when I compare my alcohols and phenols, ROH with my phenols, so definitely phenols are going to be more acidic. Right? Okay, now if I give you different phenols, what will you do? Okay, we'll see that. What can be done? For this, you need to know resonance, but I think you will be able to manage. Right? If you don't understand, please ask me. Just stop me right there and ask me. Okay, fine. So first tell me, in benzene ring, right? I have something called as ortho para directing groups, and I have something called as meta directing group. That is not what you're going to see here. But how do you decide, right? How do you decide whether a particular molecule is going to be meta directing, or a particular group is going to be ortho para directing? Is again going to be based on resonance, isn't it? Right. So maybe I will talk about that first. Then maybe we'll talk about different acids of, I mean, different phenols having different acidic strengths. Right. Fine. So I would say any group can again, even in resonance, right? Even in resonance, I can have two types of groups. One is going to be electron donating groups. The other one can be electron. Okay, I said electron withdrawing. The other one is going to be electron donating groups. Okay, two types of groups, right? So we'll see how that works in benzene ring, right? Fine. Say for example, if I put OH, for example, or say I put an NH2, aniline for that matter, right? So all these are going to be, okay, let me list some of them. Electron donating groups in benzene, right? They it can be OH, it can be NH2, it can be CH3, but CH3 is not through, I will not CH3, I'll say R generally, any alkyl group for that matter, right? These are, and even OR, ethers, right? So all these things will generally be electron donating in nature, right? Now, how do you decide whether they're going to be electron donating or electron withdrawing? Is very simple. If you find that particular group has a lone pair, okay, this is an assumption. I'll come back to this, right? So whenever you see generally that there is going to be a lone pair present, so that lone pair can involve in resonance with the benzene ring. Right? So that's why we say that they are electron donating groups, right? Say electron withdrawing groups can be, say, COOH, right? Any acid derivative for that matter, esters, what is that? Amides, what else? Acid chlorides, right? All these things, any acid derivative for that matter, right? And obviously, C double bond O's, it can be alcohol or, sorry, not alcohol, it can be aldehyde or ketone, right? So the moment you see that the carbon atom is directly in the carbonyl carbon, C double bond O is directly attached to the benzene ring, right? So definitely it is going to be electron withdrawing. So don't worry, I'll prove all this, how they're electron donating, how they're electron withdrawing, we'll prove all this. Okay, fine. So these are all the different electron don't. Oh yeah, one main thing I forgot. NO2 is a very good electron withdrawing. Okay, NO2 group, nitro group will be an excellent electron withdrawing group. Okay, so anyways, we'll see all this, how they are electron donating, how they're electron withdrawing, and because of that, what is going to happen to the benzene ring, right? All these things we'll see now, right? Okay, so yeah, so if I have OH or any of these groups for that matter, right? So I have this. Okay, I have this. Now, what do you think will happen? Now, everybody, okay, I want to know a genuine answer from all of you, right? Everybody has to answer. It's not a question from this. I'm just asking you. Everybody knows how to write resonance structures.
Sir, sorry, what structures?
Resonance structures. Do you know how to write resonance structures? Do you know how to make the bond go next bond, all these things? Do you know? I want the honest answer. If you don't know, I will teach you. If you know, then I can continue. That's why I'm asking.
Sir, I have a medium idea, sir.
Okay, fine. That again, I will take it as a no. Because like I understand, like I completely understood. I know that like most of your chemistry faculties in school wouldn't have taught you exactly. They know, but they just put the arrow marks and go. So I wanted to fully know it. So that's why I'm asking. So what about others?
No, sir.
I can partially remember. Sir.
You can partially remember. Fine. So if that's the case, I think instead of seeing this, we have to we'll actually drop this thing, right? So I will take a precedence separately, then we'll go to all these things. Okay, this is now is really a waste of time if I'm gonna talk about this. If like you can manage with resonance structures, but I wanted to exactly know how exactly we will write the resonance structures and what are the cases you can use resonance, right? So yeah, we will not see this now. I'll completely take it up later. Okay, so fine. So generally, what you have to understand is people, right? So alcohols are the least acidic, then comes your phenols, then the carboxylic acids. So this is generally the order of acidic strengths. Don't forget it. Okay, alcohols are the least acidic, then comes your phenol, and the carboxylic acids are having the maximum acidic strengths. Okay, again in for different carboxylic acids you'll be able to answer. For different alcohols you'll be able to answer the order of acidic strength. For different phenols we'll see it later. Once we take up resonance, then we'll see phenols. Is that okay? Right. Fine. So other than this, right? Other than this, I have certain other molecules also to be little acidic. Okay. So that one, I mean, that one is going to be my terminal alkynes. Okay. Now, what do you mean by terminal alkynes? Any idea? Alkynes we know. What do you mean by terminal alkynes? Hmm? Okay. You don't have to be right.
Sir,
Sir,
which is present at one carbon.
Ah, correct. So the last two carbon atoms in the chain, if they're going to have a triple bond, right? Those are what are called as. I think someone else tried to answer. It was this only, I guess.
yeah, yes, sir, yes, sir. Yes, sir.
Ah, cool. Right. So yeah, as you both are correct. So it would be the alkynes having triple bond at the end. Basically, last two carbon atoms are going to, if they have a double bond, triple bond, they're going to be called as terminal alkynes. So I'm telling terminal alkynes are also acidic in nature. Okay. Now we have to prove it how, right? Say for example, if I take this normal, the simplest of our alkynes with me, the ethyne molecule. Okay. Now ethyne molecule, now again, same thing what we do in the other acids, I remove the H plus, check for the stability of the conjugate base. So if I do that, okay, so that means this H plus can come out. Now, I don't know whether you know it, right? So this is stable. This particular thing is stable. Now, anybody want to comment on why this is stable, how this is stable? And I completely understand if you don't know exactly because it's completely understood. Anyways, you wanna guess why is it like this? Why is this why is the anion stable?
Don't know, sir.
Okay, I understand. Fine. So now let me look at this molecule. Say I have ethane molecule, okay, and say I put my ethene molecule also, okay. So I remove H plus from all of them, CH2 minus, CH minus. All these are my conjugate, assuming that these two are acidic in nature. I'm just doing it, right? Okay. So how do I decide the stabilities in this case? All of them are carbon atom. All of them. It's just that one of them is alkane, alkene, and another one is alkane. Okay. Now, how do I decide the stabilities in all these things? Right. So, people, what you have to understand is, right? So the thing is, see, it's all about the hybridization here. Okay. So I know this. So it's not about this carbon atom. This carbon atom is having the negative charge. Look at the next carbon atom. Next carbon atom is sp hybridized. Okay. Now, hope you remember how is it sp hybridized. I told you there will be something called a steric number. Steric number is equal to the number of atoms bonded to the central atom plus number of lone pairs. And you see that for this carbon atom, there is one hydrogen and there is one carbon and there is no lone pair. Steric number is 2. So when you have steric number 2, it is going to be sp hybridized. Okay, fine. So like this carbon atom will be sp2 hybridized and definitely this carbon atom is sp3 hybridized. Okay, now what you have to understand is people, right? Whenever I have more s character, right? Whenever I have more S character. I'll tell you what will be more S character. The atom will be more electronegative. Right? More and more is the S character. Right? More and more will be the electronegativity. Now you can use this, right? You can use this particular thing when I'm talking about same element in different hybridizations, like this carbon atom only, right? But carbon atom isn't different, the carbon element only, but the element is in different hybridization. Okay, so only for this you'll be able to, like, only for this kind of cases you will be able to use this particular thing. More and more is the S character, right? More and more will be the electronegativity. Okay, now tell me, in case of sp hybridization, what is the percentage of S character?
50.
50%.
Right. So I have correct. So I have one s orbital, one p orbital combining to form sp hybridization. So definitely I have 50% S character. Okay. Now when I have sp2, what is the percentage of S character?
33%.
Yes, 33.33% of S character. Okay. Now, okay, write it here. When I have sp3, how much S character?
25%.
Yes, 25%. One s orbital, three p orbitals. So totally four out of them, one out of four, one of them is S. So definitely 25% S character. Okay. So what you see here is sp hybridized atoms, sp hybridized carbon will have maximum S character and so will have maximum electronegativity. Okay, so now what you see here, if okay, one more thing, if the next atom attached to the anion, whatever, the carbon having negative charge or oxygen having negative charge, if the next atom is going to be electron withdrawing, how do I say electron withdrawing? If it is more electronegative, isn't it? More and more is electronegativity, more and more will be the electron pulling power, right? And more will be the electron withdrawing nature. Correct. So obviously, sp hybridized carbon atom is the highest electronegative among sp2 and sp3 and sp. And obviously, sp hybridized carbon is going to be a more and more electron withdrawing group compared to sp2 hybridized carbon or when compared to sp3 hybridized carbon. Is understood? So now I think you'll be able to get an answer of why the terminal alkynes are going to be a little acidic. It's because the carbon atom next to the carbon atom having negative charge is sp hybridized. So definitely the negative charge is going to get decreased because of the sp hybridization of carbon, because of the electron withdrawing group of carbon, the sp hybridized carbon. So that is why terminal alkynes are acidic. Yes. Any doubts here? Everybody understood why terminal alkynes are acidic? So definitely from these two, that is my alkenes and alkanes, this is never possible. Even you can opt for sp2 is little electronegative, but not electronegative enough to make this stable. Okay, only alkynes, and that too only terminal alkynes are going to be acidic. Okay, now answer my question. Why not non-terminal alkynes? Why not? Why am I not taking non-terminal alkynes and saying that they're acidic? If I tell you the answer, you'll kick yourself.
So non-terminal alkynes do not even have hydrogen attached to them.
Yes, thank you so much. That's the reason, right? So, for example, if I have, say, but2-ine, right? Now look at this. There is no hydrogen atom at all. So, no non-terminal alkane will have any hydrogen. Only if I have hydrogen, I can get it as H plus. So that's the reason, right? So terminal alkynes are little acidic, but please understand that terminal, we say that it is acidic, but it is very less acidic than water. Okay. Now, actually, let me give you this. So, okay. If I rewrite this little bit, the order which we already took, putting up all the acidic molecules which we saw. So the least of them all will be alkynes, that is terminal alkynes. Then comes little your alcohols, and then water, then your phenols, and then acids, carboxyls. This would generally be the order of acidic strength, right? So alcohols and alkynes are even less acidic than water, but I can make it. I can put some substituents there and make it more. But generally speaking, right? Generally speaking, alkynes, then alcohols, then water, then phenols, then carboxylic acids. This will be the order of stability, not stability, acidic strength. Okay, so I think everybody understood how terminal alkanes are acidic in nature, and yeah, that is about the acidic strengths, people. We'll solve a lot of problems. Don't worry, right? Let me complete basic strengths also, and actually let me complete all the three effects. Three effects are going to be inductive effect, hyperconjugation, and resonance. Let me complete all the things, and you'll get a very good picture. And then we will exclusively have a class. Say 2 classes also we can have for solving problems. I'll give you so many problems, and you're going to solve it. We are going to solve it. Definitely, I'm going to be there all the time. So yeah, people, you can go take your break, right? We'll be back by 11:15, right? So you can switch off your video, switch off your mute, but do not come out of the meeting. But even if you come out, you can join again, right? So I am going to switch off my video and audio, and I'll be back in 15 minutes, right? So be back in 15 minutes. Okay. Yeah.
Okay, sir.
Hope all of you are back. Okay. So yeah,
Yes, sir.
cool. So we'll continue, right? So you have finished your acidic strengths. So we go on to basic strengths. Okay, right. Basic strengths. Okay, fine, people. So first, we have to define what are bases, right? So what do you think are the bases? How do you define bases?
A compound with the capability of dissociating OH minus from itself.
Okay, that is one of the ways, right? So definitely, I have a molecule, and if I dissolve it in water, it's very important. If I dissolve it in water, and if it gives me OH minus ions, yes, it is basic in nature, right? But that kind of basis you will not see in organic chemistry, right? So none of them will give me actually OH minus. It will give, but that is not the criteria we're going to use for basis in organic chemistry, right? Fine. So that is one of the definitions. What are other definitions you know for a base? So there are substances, right, which doesn't give me OH minus, but still their pH is less than 7, indicating that they are basic in nature. Right? Again, same goes with acids also. There are acids which doesn't give me H plus, but still they have the pH values less than 7, again indicating that they are acidic in nature. So is there any other criteria other than H plus and OH minus which decides whether the particular substance is an acid or a base? Any other criteria is there? Okay, I can tell you the name. Do you know that there is something called as Lewis acids and Lewis bases?
Yes, sir.
Have you at least heard of it? Ah, okay. Someone has heard of it. Okay. I don't expect you to remember, but do you remember what do you mean by Lewis base? What do you mean by Lewis acid?
Sir, when the unshared pair of electrons can form a bond with any
Another group.
cation,
Hmm.
with any cation, it is a Lewis base.
Okay, good, fine. Lewis acid. Okay,
Which
fine. Yeah, tell me.
which can accept electrons.
Good, right? So that's the Lewis concept, people. Lewis concept of acids and bases, right? So as he said, right? So anything which can donate a lone pair, right? Whichever can donate a lone pair to some other species, and obviously donating a lone pair will be in the form of a bond, or actually it is getting donated, whatever it is, right? So whenever molecules are capable of donating a lone pair, they are going to be called as Lewis bases, right? And whichever molecule is able to accept a lone pair, they are going to be called as Lewis acids, right? So again, Lewis acids we don't have in organic, right? And what about the other one? The name that is what is that? The H plus and OH minus concept, right? That is called Arrhenius concept. Yes, good. Arrhenius concept, right? Arrhenius tells that whichever gives me H plus OH minus are called as acid base respectively. And I have Lewis, and actually I have one more. One more. Do you know what is one more concept?
Conjugate
Lowry
acid.
Bronsted. Lowry Bronsted.
Ah, exactly. Lowry Bronsted acids and bases, right? So Lowry Bronsted acids and bases are how to put it. Now here in Lewis concept, we speak in terms of electrons, right? There we speak in terms of protons, right? Say if anything is capable of donating a proton is an acid, right? See, we know what is a proton, right? So for example, if I take H plus, actually H plus is a proton, right? Hydrogen has one electron and one proton, right? So when I say H plus, the electron has been lost. So what is remaining? Only one proton is remaining, right? So indirectly, it also tells that whichever is donating H plus is an acid, right? But Lowry-Bronsted acids, we don't see much, but Lowry-Bronsted bases, whichever is able to accept a proton, is a base, right? So this is a very good example, right? Now, what can be examples for this accepting a proton? Examples can be NH3, right? NH3 will accept a H plus to form NH4 plus. So my NH3 is going to be a Lowry-Bronsted base, right? Now this can be regarded as a Lewis base also. Why? Because how this is forming is because I have a lone pair and this lone pair is going to get donated to the H plus. So again, it's a Lewis base. Donated in the sense I'm going to have a coordinate bond. We know what is a coordinate bond. Two electrons coming from one species. What is a coordinate bond? Anyways, so these are all the broad concepts of acids and bases. Lewis concept, Arrhenius concept, and Lowry-Bronsted concept, right? So we saw in organic molecules are capable of giving H plus, but you will not see them other than Arrhenius concept. You will not see acids as such, right? But when I go to bases, right, majority of the times you will be seeing only the Lewis bases. Lewis bases in the sense whichever is able to donate a lone pair is regarded as a base in organic chemistry, right? So this is the fundamental thing which you have to know, right? So moving on, right? Now, how do you decide acidic strength? Now, given that we are going to deal only with Lewis bases, right? Given that we are going to deal only with Lewis bases, right? So what will be the criteria for the basic strength here? Now, it is not going to be based on, so definitely I would say the criteria would be based on conjugate acid, right? How do you have conjugate base of an acid? I have conjugate acid of a base. Exactly opposite. After removing OH minus, whatever is remaining, or say after accepting H plus, whatever is remaining, or say after removal of the lone pair, whatever is remaining, all these can come under the category of conjugate acids of a base, right? But again, that criteria will not be using much. The main criteria we'll be using is the availability of lone pair, right? Availability of the lone pair. Obviously, right? More and more the lone pair is available. More and more is the ability of that particular species to donate the lone pair. First of all, the lone pair should be available. Available, it is going to be there. But again, based on electron donating and electron withdrawing rules, I'll be able to tell, okay, the availability of lone pair is decreased or increased. Based on that, we'll be able to tell, right? So first and foremost criteria for deciding the basic strength is going to be availability of lone pair. We'll see examples, don't worry, right? And the next one can be the concept of conjugate acid, stability of the conjugate acid. So when I write Ca is the conjugate acid. Okay, fine. So we look into examples, and the best examples I can take is going to be my amines, because amines are generally basic in nature. We know that, right? Okay, so let me take a primary amine, secondary amine, and a tertiary amine, right? And again, I hope for some of you this chapter would have been taken in your school. See it again. So let me compare, starting with ammonia. I have ammonia, right? And say I have a primary amine. I have a secondary amine. Bear with me, I'm putting it here. And say I have a tertiary amine. Right? All of them have lone pair on nitrogen. No doubt about it. Right? All of them have lone pair on nitrogen. So all of them can donate this lone pair to some other species behaving as Lewis bases. Okay. Now, if I want to compare, if I want to arrange them in the order of basic strength, right? How do I do it? As I said, it is going to be based on the availability of lone pair. Okay. Now, keeping all this in mind, okay, can you tell me out of all this, which is having a maximum basic strength?
Tertiary amine.
Good. Why?
Stability of carbon atom.
Stability of carbon atom. No, answer is correct. Reason is not right. Anybody wants to give a reason? Why? Tertiary amine is the answer. Tertiary amines are the ones going to be most maximum basic. Any answers? Why? Use inductive effect. Simple, right? So you know that I have 3 electron donating groups in tertiary amine, right, which is going to increase the availability of lone pair on nitrogen. Now it is not about charge, it is about the lone pair, right? So there is going to be increase in availability of lone pair because of the 3 electron donating groups present, right? And obviously, if I go to this case, I have only 2 electron donating groups, and if I go here, I have only 1 electron donating group. And obviously, here there are no electron donating groups. So if I want to make sure that if I want to arrange them in the order of basic strength, right, the order would be this is the most acidic, and most basic, then the secondary amine, then the primary amine, and the least of all basic would be ammonia. Okay. So again, I repeat, it's all about the availability of lone pair. If you have an electron donating group, that is really going to increase the basic strength. Now, obviously, if I have anywhere I have an electron donating, I put a chlorine atom here, I put OH here, something like that. Again, it is going to decrease the availability of lone pair, decrease the basic strength. That is what is going to happen, right? Now, what you see here, so how can I put it in simple words, is ammonia is less basic than primary, than secondary, and tertiary is the one which is having maximum basic strength, right? This is for amines. Now, especially, this will work only in gaseous phase, right? This will work only in gaseous phase. Okay, now the phase matters, right? So if it's in gaseous phase, the only criteria we can use for deciding the basic strength is the availability of lone pair. There is no other criteria which we can use, right? But if I go for aqueous phase, if I'm going to dissolve these compounds in water, right? Now, in that case, oh yeah, this is the criteria. This is one of the criteria. But other than that, the stability of the conjugate base or the conjugate acid also come into the picture. Okay, so we'll see how, right? So till now, any questions? Till now, we understood that tertiary is having the maximum basic strength and ammonia is having the minimum basic strength because of electron donating group present in tertiary. That's it. Okay, right? So this is in gaseous phase, right? Because in gaseous phase, there is no other criteria other than the availability of lone pair. That is the only criteria. Okay, now we'll go for what happens when I dissolve them in aqueous phase and dissolve them in water, right? So if I dissolve them in water, right? So please understand, people, water is an amphiprotic substance. What do you mean by amphiprotic substance? An amphiprotic substance can donate H plus as well as accept H plus, right? Now, how will you decide that? So water, I told you, can remove H plus. Again, if I can even write this equation if you want. 2 moles of water molecule can give me 1 mole of H3O plus, and the other one can give me OH minus. Or I can write it as 1 H2O gives H plus, and the other one is going to be OH minus. So these are what are called as what is that? Amphiprotic substances. Right? Amphiprotic means which are capable of donating H plus as well as accepting H plus, or donating H plus as well as donating OH minus, something like that, right? So now, how do you decide? How do you decide whether water is going to act as an acid or a base? Is going to depend on what other substance you're going to you have along with water, right? Say for example, if I have an acid, say HCl dissolved in water, right? So obviously HCl is a better acid, so that will give me H plus, and in that case, water will accept OH minus. Sorry, accept H plus, right? HCl will give H plus, water will accept H plus, right? Now, what happens if I dissolve a base? Now, in that case, H2O is a better acid, right? So that will give me H plus, and the base will accept the H plus, right? And that's exactly what we are going to see here. Okay, so the moment I dissolve NH3, for example, in water, right? What do you think is going to happen? From this, H plus is going to come, right? And it is going to get accepted here to form NH4 plus. And what will be remaining? If I remove H plus from water, what is remaining? OH minus is remaining, right? So obviously NH4 plus OH minus will give me ammonium hydroxide. This again, right? So that is one thing. Say for same thing will happen if I dissolve, say, the primary amine or secondary amine or tertiary amine in water, right? Now it is all about the stability of this conjugate acid. Not all about it. Like again, the second criteria. First criteria is obviously there. According to the first criteria, we already decided which will be the what will be the order of basic strength, right? If I look at this, right, this is my conjugate acid after accepting H plus. What is there? It's my conjugate acid. So the stability of the conjugate acid is also going to play a major role in deciding the order of basic strengths. Okay, so let me write all the conjugate acids possible for primary, secondary, and tertiary. Right. So obviously for ammonia, it is NH4 plus. For primary, it would have been CH3, NH3 plus, say for NH2, CH3. This is for secondary amine, and for tertiary amine, okay, I have a CH3 here and a positive charge. Okay, right. So these are all the different conjugate bases. Sorry, conjugate acids I have for the bases. Right. Now, how do you decide the stability? And definitely you can use inductive effect. Definitely you can say that electron donating groups are there and stuff. But more than that, right? More than that, the one which is going to give me stability here is the concept of hydrogen bonding. You must have heard this term so many times, right? Hydrogen bonding, this is capable, that is capable, all these things. So hydrogen bonding is the one, right, which is going to decide the stability here for the conjugate acids, which I have, right? Okay, fine. So we have to discuss first about the what is that hydrogen bonding. Then only we can go for this, right? Fine. So we'll take some 2 minutes. We'll come back to this. I'll drop this part now. Again, I'll write this. And then we'll explain based on hydrogen bonding, which is more stable, which is less stable. Right. For now, we'll concentrate on hydrogen bonding. Okay. So you'll again study this in your chemical bonding chapter, but we cannot wait till that because so many times we'll be using this. Okay. So hydrogen bonding comes under a special type of bonding called as secondary bonds. Okay, so all bonds in chemistry can be classified into two types. One are what are called as primary bonds, the other are what are called as secondary bonds. Okay, now what is the basic difference is primary bonds are actual chemical bonds, right? In the sense, okay, now we'll go back to some old theory, Dalton's law, Dalton's atomic theory. Okay, now in Dalton's atomic theory, if you can remember, one of the points, one of the postulates told by Dalton was atoms undergo some kind of rearrangement during a chemical reaction. Right? That's a simple statement he said. Atoms undergo some kind of rearrangement during a chemical reaction or during a chemical process. Right? Now, same thing can be applied to bonds. Obviously, a bond is broken or a bond is formed during a chemical reaction, isn't it? Say reactants in the case of reactants, bonds are broken, or like say products, the bonds are formed, or opposite. Anything can happen, right? So obviously, when a bond is broken or a bond is formed, there is going to be rearrangement in the atoms, right? Now, what is the rearrangement? Can you guess? In an atom, what is the rearrangement which you are talking about?
Sir, it forms secondary bonds.
No. What I'm asking is, right? So Dalton said that there is going to be some kind of rearrangement during a bond breaking or a bond making process, right? I'm asking, what is the rearrangement you're talking about? In an atom, there is something which is going to change. What is the thing which is going to change?
Electron configuration.
Wow, yes, that's the answer. Definitely, the thing which is going to change is the electronic configuration, right? So why is it that sodium is able to form sodium plus and forms a NaCl compound? Is because sodium is going to lose an electron and thereby chlorine will accept an electron to form NaCl. So basically what you see is that I am going to have the rearrangement which the Dalton was talking about is basically going to happen in the electronic configuration of an atom, right? That's what is being changed. That's what is being told as a rearrangement, right? So in case of your primary bonds, actual chemical bonds, the electronic configuration is completely changed, right? The electron is completely transferred or completely accepted or completely shared in case of a covalent bond. So those things come under primary types of bonds, a complete rearrangement, 100% rearrangement of the electronic configuration, right? But when I go for secondary bonds, yes, there will be some rearrangement, but there is not going to be complete rearrangement. There is going to be partial rearrangement happening. Okay, that means the electron will displace little bit from the atom, but it is not completely lost or completely gained or completely shared. No, that is not how it is happening. It is partial, right? So hydrogen bonding comes under the category of secondary bonds. I have so many other types of secondary bonds, say dipole-dipole interactions, dipole-ion interactions, van der Waals forces, right? So all these things comes under your secondary bonds. Again, we'll speak about this in depth when I go for chemical bonding. Okay, for now we'll concentrate only on hydrogen bonding. Okay, so for hydrogen bonding to happen, people, I require two things. Okay, so first one are what are called as hydrogen acceptors, right? The other one more what are called as hydrogen donors. Okay, so for hydrogen bonding to happen, these two should be there. Okay, say I know the best example I can give you is water. Right, now water, I know, like water is a special thing which, because it is capable of it is capable of behaving as both of them. It can be a hydrogen donor, it can be a hydrogen acceptor, but again we have to understand what is the criteria for a molecule to be a hydrogen donor and what is the criteria for a molecule to become a hydrogen acceptor. We'll see that now, right? So for a molecule to be a hydrogen donor, right, the hydrogen atom should be attached with a highly electronegative atom, right? The hydrogen atom should be attached with a highly electronegative atom, and I'm going to have only three things, right? Only three of the elements which are capable of being hydrogen donors. So the bonds can either be a OH bond or a NH bond or a FH bond. Only these bonds are capable of being hydrogen donors, because the oxygen, nitrogen, and fluorine are the most electronegative elements in the periodic table. Right, now other things, Cl, all these things can have, but I'm not going to call them as hydrogen bonding. Only if I have OH bond, NH bond, and FH bond, right, those things will come under hydrogen donor capabilities. Okay, now why is this happening? Is because obviously it's obviously because of the polarity difference, right? So obviously it's all about the del negative and del positive which I'm going to have on the electronegative atom and the hydrogen, right? So it is all based on that. Now we'll see how exactly the hydrogen bond is formed. For now, the first criteria is that I need to have hydrogen donors. And what can be hydrogen donors? If you see that the hydrogen atom is attached to any of these three elements, oxygen, nitrogen, or fluorine, yes, they will be able to. They will be able to behave as hydrogen donors. Very, very simple. Okay. Now for hydrogen acceptors, it's still more an easier concept. It's very simple that the only criteria is that lone pair must be present. Right? A lone pair must be present on some atom. Right? Okay. Now, if these two I have, so if I have a hydrogen donor and if I have a hydrogen acceptor, I'll be able to have hydrogen bonding. Okay. Now we'll take an example. Okay. Now let me take the example of HF molecule, hydrogen fluoride molecule, and we'll see how is it happening. Okay, now please understand, people, if I have one HF molecule, right, the bond between H and F is a primary bond. Yes, definitely, it's going to be a covalent bond, right? But I have one HF molecule, another HF molecule, and the interaction between them is a secondary bond. And in this case, it is going to be a hydrogen bond. Okay, so whenever you talk about molecular interactions, I have one molecule, another molecule. The molecular interactions will generally come under your secondary types of bonds. But atomic interactions, I have hydrogen atom, fluorine atom, and that case we'll be speaking about primary bonds. I hope you get the whole picture, right? So we'll take HF as the example, right? So if I take HF as the example, definitely it comes under the category of hydrogen donors, because I see that the hydrogen atom is directly attached to a highly electronegative element, that is fluorine here, right? So definitely there will be some separation of charges happening, del negative and del positive, right? Okay, and looking at the second category, second criteria, that it has to act as a hydrogen acceptor also. Yes, fluorine has lone pair, it has 3 lone pairs, right? Okay, now I take one of the HF molecule, and if I take another HF molecule, right? So again, here also I will have del positive, here also I'll have del negative, again lone pair is there. Okay, Now, for you to visualize hydrogen bonding, there are two ways of visualization, right? So what is the first way? You can easily see that there is a del negative, there is a del positive. So I can have an interaction between the del positive and the del negative. This is my hydrogen bond, right? Or the second way of visualizing it is you can say that the del positive of the neck of the second molecule of HF is going to interact with the lone pair present on the fluorine of the first molecule. Either way, so basically lone pairs are negatively charged. Electrons are negatively charged. So the lone pair is definitely negatively charged. So the interaction is going to be between the del positive of this hydrogen and the lone pair on the other molecule of H plus, and fluorine's lone pair is what we're talking about. Okay, so either way, you see that it is going to be the what is that, the interaction between del minus and del positive, or say del positive and the lone pair on the hydrogen acceptor can be regarded as hydrogen bonding, and the more correct way is going to speak in terms of lone pair. Okay, so more precise way would be to talk in terms of lone pair and the del positive interaction. So this exactly is what is called as my hydrogen bonding. Okay, so same thing can happen with water molecule also. So again, so you see that in this case, the HF molecule acts as both hydrogen acceptor as well as hydrogen donors, right? But again, water is also capable of that. Why? We'll see. Right, so if I take water molecule, right, again you see that it can be acting as hydrogen donor, because you see that the hydrogen atom is attached to a highly electronegative element, that is oxygen, right? And this can also act as hydrogen acceptor, because I know oxygen atom is going to have a lone pair, two lone pair, right? Okay, so if I take one more water molecule, so again a del minus with a okay, I'll write del minus down with a lone pair, two lone pair, and hydrogen is going to have a del positive, right? So same way here, del positive, del negative, right? So between two water molecules, how can I connect it? Say the lone pair on this oxygen and the del plus on this hydrogen can have an interaction. Same way, this hydrogen and the lone pair, again, this is having a del positive, the interaction here, right? So this is exactly what is my hydrogen bonding. Okay, secondary types of bonds. It's not an exact bond, but again, right? So what are the consequences, right? What are the consequences of having hydrogen bonding, right? So when I have hydrogen bonding like this, right? So generally when I go for phase transitions, for example, if I want to convert a liquid to a gas, right? When I want to convert a liquid to a gas, so what you're trying to do, so I know liquid particles are little closely packed, and gaseous molecules are very, say they're very much far away from each other, the gaseous molecules, right? And obviously the force of attraction in liquid molecules are a little higher, and the gaseous molecules have the least force of attraction between the gaseous molecules, right? So what you're trying to do when I go for boiling, I am trying to increase the intermolecular space and decrease the force of attraction, so that liquids will become into vapor phase, right? Now if you're gonna do that, right, now if I have just this molecule and there are no interactions like this, there are no hydrogen bonding, there are no secondary bonds, right, definitely it will be very easy for me to say increase the distance between these gaseous molecules, right? But since I have these interactions, you have to supply more energy, right? You have to supply more energy for these to go far away from each other, and thereby they have to go into the gaseous phase, right? Say for example, since water molecule is capable of forming hydrogen bonds, that is why it is having a 100 degrees Celsius as the boiling point, right? But if, for example, if hydrogen bonding was not there in water, it will not be maybe 100 degrees Celsius, it will be around only 70 or 60 degrees Celsius, right? So the thing is, for boiling point considerations, right? So there are two criteria. One is that the molecule which is having a higher molecular mass, right, will have generally higher boiling point, right? So if I compare it with CH3OH or say CH3CH2OH, this is my ethanol, right? So definitely ethanol has more molecular mass than water, is it not? Water is only having 18, so this is definitely going to be more than 18, right? But if you look at the boiling point of alcohol, boiling point of this alcohol will be around say 74 or 78 degrees Celsius, right? But for water, I know is going to be what to say, 100 degrees Celsius, right? Even though this has more molecular mass, right? Now, how do I explain this? Right? It is going to be explained on the basis of extent of hydrogen bonding. Now, please understand, people, this molecule is also capable of giving hydrogen bonds because I have a OH bond which can act as a hydrogen donor, and oxygen atom is having a lone pair, so this can act as a hydrogen acceptor, right? But what you see here is that between two water molecules, right? Between two water molecules, I can have two interactions, like this hydrogen, this oxygen, this hydrogen, this oxygen. So the number of interactions, the number of hydrogen bonds between two water molecules is greater when I compare here because I have only one hydrogen here. Even though I have two lone pairs on oxygen, but there is only one hydrogen here. Is it not? Right? So definitely the extent of hydrogen bonding is less, extent of hydrogen bonding is greater in water. And that's why you see water molecule is having a higher boiling point. That is 100 degrees Celsius, and this is having only 74 or 76, something like that. Okay. So that is one of the consequences of having hydrogen bonding. Right? And other consequences would be the solubilities. Say, for example, let me take an example. I know I'm deviating from the topic, but it's a little important. That's why I'm deviating. Right. Say, let me take an example. Let me take an example of an ether. I have CH3, OCH3. Right. Now tell me, is this capable of forming hydrogen bonding? Is this molecule capable of forming hydrogen bonds? Yes or no?
No, sir.
No. Obviously. Why? So you can say that yes, I have oxygen to be having lone pair, so you can access hydrogen acceptor. But there, you can say that the hydrogen atom is there, but it is not attached to oxygen atom. So this can itself, if this only molecule is there, it cannot form hydrogen bonding, right? And accordingly, that ethers will have very less boiling points, even lesser than alcohols. Okay, so now, but that is not what you're speaking about. Now, when I'm going to dissolve this particular thing in water, okay, now what is going to happen? Now, water I know is definitely capable of uh, undergoing hydrogen bonding, right? Now, in this case, if I dissolve this in water, I can have an interaction between the del positive of this hydrogen and the lone pair on the oxygen of the ether molecule, right? So since you have strong interaction between a solute and solvent, more solubility is going to happen, right? So this is another criteria, right? So one molecule is not capable of hydrogen bonds by itself, but if that molecule is capable of hydrogen bonding when it dissolves in water, then definitely the solubility is going to be higher. Okay, so the first consequence was boiling points, and the second consequence would be the solubility. Higher solubility will be there if I'm capable of undergoing hydrogen bonding, right? And other than this, I can have two types of hydrogen bonding. One are what are called as intermolecular hydrogen bonding. The other one is what is called as intramolecular hydrogen bonding. Okay, so it's very simple. You can understand what do you mean by inter-school competitions and intra-school competition, right? So inter-school will have so many schools participating. So your school, so many other schools will be participating for a competition, say a sports event or some cultural event, right? So many schools will be participating, right? But here, within your school, you will be competing only with your schoolmates, right? So that's about my intra-school competition. The same goes here, right? If I see that for hydrogen bonding to happen, right, I require two molecules, say two H2O molecules, or like say one ether molecule and one H2O molecule, like this. Two different compounds or two different compounds, not necessarily two numbers of compounds. It can be same or different, right? Whenever you require two numbers of compounds for the hydrogen bonding to happen, it is going to come under intermolecular hydrogen bonding. So till now, whatever example you saw, H of H2O, this one, all these comes under intermolecular. Okay. Now intramolecular, I don't require two compounds. I don't require two molecules in the same molecule, right? There's only one molecule, but in the same molecule, some kind of hydrogen bonding is possible. Okay, we'll take an example. You would have maybe studied this in organic, right? Let me go for this. What about intramolecular hydrogen bonding? Right. So let me take your orthonitrophenol. Ortho position, I have a nitro group. Okay. Now, if you look at the structure properly, say I would have had a double bond O and a coordinate bond with another oxygen. Okay. So obviously, this oxygen atom has lone pair, two lone pairs of steel actually, right? Now I don't require two molecules for me to undergo hydrogen bonding. Now you see that this hydrogen atom is capable, again, is having a del positive, del negative. So I can have an interaction between the del H plus and the oxygen's lone pair on the nitro group, right? So do you have two molecules? No, you just have two groups in the same molecule, which one is going to act as a hydrogen acceptor, the other one is going to act as a hydrogen donor. So yes, this is an example for intramolecular. Within one molecule itself, hydrogen bonding is going to happen. Okay. Now the next question is, sir, which is stronger, intermolecular or intramolecular? Blindly always say that intermolecular is stronger than intramolecular hydrogen bonding. Right. So how do I put it? Is, say, for example, if I compare orthonitrophenol with paranitrophenol. Okay, orthonitrophenol and paranitrophenol. So there is no way that this and this can interact because the distance is very far apart. Right. But if I say, if I have one more molecule of this, right, then I can have, say, I put it like this if you want. Okay, how do I put it? Right. Right. Say I can write it like this. Right, I can write it like this. Say now this also I can write it like this. Right. Say again I can have interaction between these two and interaction between this two. Okay, now this is an example for intermolecular, right? So definitely intermolecular is going to be stronger than intramolecular. And how do I prove it? Is when I compare the boiling points. Okay, so the orthonitrophenol, the last case which we saw, is going to have a lesser boiling point when compared to paranitrophenol, because in paranitrophenol I have intermolecular, and orthonitrophenol I have intramolecular. Yeah, orthonitrophenol I have intramolecular hydrogen bond, right? So these are the different things which you know about hydrogen bonding. Okay, now why did we start all this? Is for deciding our basic strengths of amines in your aqueous phase, right? So let me go for it. So it's all about extent of hydrogen bonding. I can give you one example if you want. Okay. No, we'll actually directly go for the example, right? So any questions, people? Any question on hydrogen bonding? You want to ask me something?
No, sir.
Okay, fine. Cool. So we'll move on to the concept which we already started, right? Which we started now. So let me write the conjugate acids of the bases. Okay. So for ammonia, NH4 plus, then for primary amine, it would have become CH3 NH3 plus, and for this is my secondary amine. And this is my tertiary amine. Okay, cool. Now, obviously, the first criteria stands the availability of lone. Now, this availability of lone pair will come before even this, because now the lone pair is not there. None of them has lone pair here. That criteria is already gone. In the sense, before accepting H plus, then you have to look for the what is the availability of lone pair. And obviously, we know the result. The result is tertiary is having more availability of lone pair than secondary, and secondary is having more than primary, and primary is more than ammonia. That we know, right? Now we'll use the conjugate stability of conjugate acid constant to decide the stabilities. Okay. Now the stability we will not be able to decide with the help of the amount of positive charge and amount of negative charge. How can I speak it with the help of hydrogen bonding? Okay. Now, see, please understand that all these things cannot act as hydrogen acceptors. Yes. Why? Because none of them has lone pair. None of the nitrogen atom here has lone pair. Right. But they can act as hydrogen donors because nitrogen atom is there and I have a hydrogen atom attached to it. A highly electronegative atom is attached with hydrogen. So definitely they'll be able to undergo hydrogen. They'll be able to act as hydrogen donors, but not hydrogen acceptors because I don't have any lone pair. But this can be hydrogen donor to the water molecule. Just we saw how examples in the ether and water example, high solubility will be there. Just like that, here the NH bond, right, which is going to act as hydrogen donor, can donate the hydrogen to the oxygen whose lone pair on water. Right, because water can act as both hydrogen acceptor as well as hydrogen donor. Now, in this case, this acts as hydrogen donor and water molecule acts as hydrogen acceptor. Now, so everything is capable of doing this. Everything has an NH bond, right? It is going to act as hydrogen donor and water is going to be able to, water is going to act as hydrogen acceptor. So in all of them, hydrogen bonding is there, no doubt about it, right? But the question is, which is going to have more hydrogen bonding? In which case, I have more extent of hydrogen bonding is the question, right? Now you think and tell me, out of these four, which will have maximum extent of hydrogen bonding with water? Which will have maximum extent of hydrogen bonding with water, which will have more hydrogen bonds with water. Guess. If you don't know the answer, please guess. I'm not going to judge you.
NH4 plus.
NH4 plus. Okay. Any reasons?
No, sir.
Okay. Answer is correct. NH4 plus is the answer, which is capable of forming maximum hydrogen bonds. What is the reason? Anybody wants to give the reason? Now that you know that that's the correct answer. Now, if you logically think, you'll get the answer. Now, given the answer is known, NH4 plus is the answer, which is capable of forming maximum hydrogen bonds. What is the reason?
So the extent of hydrogen bonding is greater because there are more number of hydrogen atoms.
That's it. Very, very simple. Right. So obviously in NH4 plus, I have 4 hydrogen atoms which can act as hydrogen donors. Right. So here I have 4, here I have 3, here I have 2, here I have only 1 hydrogen atom which is capable of being a hydrogen donor. So definitely, which will form stronger hydrogen bonds with water would be my ammonium ion, then my primary, then my primary, secondary, and the least ability for forming hydrogen bonds with water will be for tertiary because it has only 1 hydrogen which can act as hydrogen donor. Very simple, right? So obviously, more and more is the hydrogen bonding, more and more is the stability, right? Because this positive charge is going to get little decreased because of hydrogen bonding, right? So if I just take hydrogen bonding into the picture, right? So obviously, if I check for the stability of the conjugate base, NH4 plus, or if I just give rankings to this, I just remove the numbers here, right? The first rank goes to this, second rank goes to this, third rank goes to this, and the least stable conjugate acid would be this or tertiary, right? So don't you realize that whatever we got the result for the first case, that is based on the availability of lone pair. Availability of lone pair was maximum for tertiary, right? But when I then compare the stability of the conjugate acid and water, that tertiary turns out to be the least stable, and ammonium ion, which was the least basic with respect to the availability of lone pair, now due to hydrogen bonding is coming out to be the maximum stable conjugate acid, right? So exactly opposite of whatever you saw. Okay, now how will you decide? Right? How will you decide So gaseous phase, no problem at all. Gaseous phase, the only criteria is availability of lone pair. That we have done, right? But when I go for aqueous phase, availability of lone pair as well as the stability of the conjugate base matters. Okay, so in that case, you have to combine both these things and then eventually get a result, right? So you wouldn't have to do anything now. I'm going to give you the answer for this. Okay, the answer is secondary will be the maximum basic one, and then comes tertiary, then comes primary, and then comes ammonia. So this is for aqueous phase. Okay, secondary will be more basic than tertiary because secondary is having both effects to be little higher. It is having more availability of lone pair also, and secondary is having reasonable amount of hydrogen bonding also. That's why secondary comes. Then tertiary because that the availability of lone pair effect dominates, right? Then comes your primary, and the least is for ammonia. Okay, so ammonia is common both in aqueous phase as well as in your gaseous phase. But other three things will change. Last case, the order was tertiary, secondary, primary. Now in this case, secondary, tertiary, and primary will be the answer. But this will change, people. This will change depending on what is the alkyl group I have here. You just have to know two things. I'll not make you remember so many things. This is for methyl groups. You can see all the things are methyl groups. Right. If all the things are ethyl groups, oh, I'm sorry, this is exactly opposite. Primary, then tertiary. Okay. So if it is going to be ethyl groups, okay, so ethyl groups will have this one: tertiary, sorry, secondary, tertiary, primary, and then ammonia. So it's all about this is going to dominate. So it's all. I know ethyl groups are more electron donating in nature than methyl groups. So that's why the tertiary comes here after secondary. And in this case, since the methyl groups, the hydrogen bonding dominates. So that's why primary comes before tertiary. Okay, you have to remember this, people, right? In aqueous phase, methyl will have methyl. If at all the alkyl groups are methyl, this is what will be the answer. And for it, if at all the alkyl groups are ethyl groups, this is what will be the answer. And to not worry, nobody is going to ask you other than the combination of this, say one methyl group, one ethyl group, or say different other different alkyl groups will not be asked in the examinations, right? So and just be understood. So if the question doesn't tell you anything about the phase, they don't tell you whether it's aqueous phase or gaseous phase, by default, it is gaseous phase. Okay, if they don't tell you anything regarding the phase, right? By default, it is going to be gaseous phase. Unless and until told that it is aqueous phase, we will not take any of this into the picture. The only criteria is availability of fluid. Okay, right? Any questions, people? Any questions from all these things that we saw? Hope everybody understood. Right? Okay. So now we have considered aliphatic amines. Right? Now what if I go for aniline? Okay. There, resonance will be coming into the picture. But again, I can just tell you what is it going to be. It's very simple only. Now, what do you think, people? I have an aliphatic amine and I have an aromatic amine like aniline. Like aniline, I know the structure. Aniline. And say if I compare it with a primary amine or a tertiary or a secondary, whatever it is, aliphatic amine, what do you think? Which is going to have a more basic strength? Again, if I don't tell you anything about the phase, it is just going to be the availability of lone pair. Yeah. So you think and tell me which will be having more basic strength. I even gave a clue. Reference is the clue. I don't have no reference factors. How to write that? Nothing is required. Just go for the availability of lone pair. Yes? Guess? Who wants to guess? Are you afraid because I'm going to ask you the reason? You can tell me that you don't know. I don't mind. What is the guess? Okay. Then I have to make some voting. So how many of you think aniline is the one which is going to have more basic character? Let me count.
Aniline.
Aniline, 1. Then, okay. Only one vote for aniline?
Aniline.
Nobody? Okay. Okay. 2. 2 anilines. Fine. What about how many of you say it's going to be the RNH2? Say the primary end. Sorry. Yeah. So how many of you say it's RNH2? Nobody. You have to give a guess. It's compulsory. Okay. It's just a voting. No, you are exactly like Indian citizens, right? You like it's like you talk about so much government atrocities and they don't do anything and all that. But when it comes to voting, you don't go and vote. Like, you are not eligible to vote yet. But still, it includes me. Even I'm 18, more than 18 years old. I have never still voted yet. Right? So we are just proving that we are Indian citizens. We want democracy, but we don't want to vote. Anyways, yeah. So basically, it's not going to be a democracy here. It's going to be a dictatorship. Now it's compulsory for everybody to give a guess. So 2 people told me that it is going to be what is it, onion. So I want to know what about the others? What about others' perspective? Tell me. And RNS2. What do you think? I mean, how many of you think RNS2 is going to be more basic? Put it in the chat box if you don't want to say.
Sir, I think it's aniline.
Okay, so aniline has 3 votes now. Okay. Harish, it's basic. What is basic? RNH2. Okay, so RNH2 for 1. Sanjana says aniline. Okay, so I have 4 votes and 1 vote for RNH2. Okay, one more person is missing, I guess.
Aniline, sir.
Okay, so again, 5 votes for aniline and 1 vote for RNH2. So again, we are proving that we are Indian citizens, right? How? You want to guess how you are proving that Indian citizens?
You voted the wrong.
Exactly. Majority of you have voted, elected a wrong person to lead this country. Not majority of you, majority of us, right? So the answer is the minority. So definitely RNH2 is the one which is more basic. Not only RNH2, like any aliphatic amine is generally going to be more basic than NH2. I mean, aniline for that matter. Okay, now why? Why is the question. So the answer lies in resonance. People look at this. I have a lone pair, and this lone pair is not even available on this nitrogen. It is involving in resonance here, right? But do you think anything is going to happen like that? No, I just have electron donating groups. Basically, the availability of lone pair is freshly 100% available on this nitrogen. But on this nitrogen, this lone pair is not available because it is involving in resonance. Right? So that is the reason why aliphatic amines are more stable, more basic than your anilines or aliphatic aromatic amines. Okay, so this will keep in picture whenever they talk about gaseous phase, i.e. the maximum basic is secondary, tertiary, primary, ammonia, then least would be for aniline. Right? So this would be the order of basic strength for all the nitrogen containing compounds. This is in gaseous, obviously. Liquid phase, I mean aqueous phase, you know how to do it. And they will not ask you all this aniline around it. Even if it's in the aqueous phase, aniline is still going to be the least. Don't worry about it. Okay, so I think we have to solve a lot of problems. I have to teach you hyperconjugation and resonance, and then we'll move on. Right, we'll do a lot of problems. I think I'll take just maybe one more class for complete. One more class should be okay, most probably. 1 or 2 more classes for hyperconjugation resonance together, right? And then I'll go for what is that? Your problems. and I think this chapter will be over. Anything else is left out? No. So this chapter will be go out, and then I'll be going for organic reactions. All these things, what you have studied, you're going to use it in deciding what will be the product and understanding how the product is forming when I go for hydrocarbons. Hydrocarbons is where you will see only reactions, reagents, mechanisms, and all these things. So in 2-3 classes, I'll be completing this chapter, general organic chemistry, right? And then right away move on to hydrocarbons, right? So yeah, almost it's time. So any questions, people? Not regarding the subject or anything else? Are you guys like okay? Tell me, how many of you are practicing problems? How many of you started practicing problems?
So it started. Exams just
You
got
started.
over.
Okay, so for you exams got over. So like problems, unless I'm asking about JEE level problems, not your
Yes, sir, yes, sir. DP.
subjective questions. Okay, good. DPP you got?
No, sir. Some material I have, sir. That I just go through.
Okay. So make sure, see, the thing is, whenever you're going to buy a material for problems, make sure they have solutions for all the questions. Like that, you buy these things. Because if you don't know, right, so you can just look back and see how they are doing it, right? But if you don't have the solutions with you, you have to go undergo a lot of, you can ask your faculty, maybe look at the net. So many stuffs are there. Again, obviously, if you don't understand, even after looking at the solution, you're always welcome to ask me, right? And see, people, I have been included in the group which you all are there, right? So if at all you find any question, just like when you're doing it, you're not able to answer it, click that question and just put it there. Whenever I see it, I will answer those questions. Or you can even directly send it to me if you don't want to send it to the group. You have my wait, now I am in the group, so you know my number, but I should have given it at the long back. So my number is this. Okay, 8939219916. This is my number. So you can always WhatsApp me personally regarding anything for that matter, not only regarding chemistry, say preparation or even your personal problems, right? Right, so anything is fine. So yeah, people, they can go. They can go have your lunch. I think it's taken long time, right? So yeah, if there are no questions, we can wind up, right? Is there any other question?
No, sir.
So I assume, okay, cool. So I assume that there are no questions. Thank you, people. Thank you for spending your time. Bye bye. We'll meet again next week.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.